All right, welcome to part 3 of the pump up for electricity for the AP exam. What we talked about last time is the object of our electric force, electric field, electric potential energy, and electric potential, V, all for uniform fields. And you kind of see that at the top of the diagram here. That was what we left off. The red boxes show the equations that are given on your equation sheet, and the other relations are ones that you need to know and you need to be able to reason through. Now the relations for force, field, potential, energy, and potential are a little bit different for point charges, and that's what we'll take a look at now. And we want to start with our relationships for the electric force between two point charges. Now, in the first place right here, we might ask ourselves, what's the force acting on the particles? Sometimes they'll say, what's the force between the particles? But it's better to ask the question to be specific about which particle you mean, which usually means labeling the particles. So in this case right here, we just call this one number 1, and we'll call this particle 2. And then we ask the question, what is the force on particle 2 by particle 1? And since these are like charges, we know that that will repel. Now the magnitude of this force we could label as the electrical force on 2 by 1, something like that. Now we know that the magnitude of this force is going to be the same as the force, electrical force on 1 by 2. And that's just because of Newton's third law. In other words, even if one of these charges was 10 times the charge of the other one, the forces would be equal and opposite in direction. The direction being determined by whether the charges are like charges or unlike charges, and then finally the magnitude of the force being calculated by our equation for electric force for point charges, which is our K, Q1, Q2, divided by R squared, where R is the distance between the centers of our two particles. So it's some kind of distance here. Now if you have some kind of an object, let's say a ball that's charged, you can consider all of its charge as being concentrated at its center when you do this equation. So it's the distance between the centers of the two objects. And this is the equation that you're given on the equation sheet. There's a slight difference in the way they represent the value K, but if you look at your table of constants on the sheet, you'll find out that there's a definition for K, 9 times 10 to the 9th, that looks in the formula a little bit different, but it just means the value for K. That's our equation for the electric force. All right, so we might ask ourselves, to complicate things now, we might ask ourselves, what happens when we add extra particles? So let's just say that we still have this charge here. This was our, and this will also be a positive charge located at this location. And if we were to go through our numbering again, we'd have our charge 1, we'll still call this our charge 2, and we'll give this the name charge, just charge 3. And now I want to know I still want to know the total force on charge 2. How would we do it in this case? Well, it's pretty clear that charge 2 still has a force on it by charge 1. It would be something like this, the electric charge on 2 by 1. It's going to point in the same direction as it did above. But now what we've done is on 2, there's also an attractive force, something like this, that we might label the force on 2 by 3. And now we ask the question, how do we find the total force on our charge 2? And of course you should realize here that we're going to have to do some sort of a vector addition. Now that vector addition here is going to, here let me clean this up a little bit so I have a little more room to write. I'm going to move this off to the side here. Let me see. We'll call that the force on 2 by 1, the electric force. All right, so what we want to do here is we want to do this vector addition. And the one way to do it is graphically, is basically to slide, let's say, this vector such that its tail lines up with the head of the other vector. And if I were to redraw that vector like this, it would look a little something like this, right here. And now to get my resultant vector, I go from my beginning point to my ending point, and I get some kind of a force there, which now is my force total. So that vector is a resultant force or a total force because of the two vectors that are acting on charge 2. Now, that's just the graphical way to do this. How would I do this mathematically? In other words, find the magnitude of the total force on charge 2. Well, if you remember back from our vector addition instruction, you'll know that what I'm going to have to do here is I'm going to have to do some components. And so what I'm going to do here is let me get it myself back to where I just have my, there we go, my original vectors and my resultant vector look like this. And you can kind of see to add those two vectors together, I'm going to have to do something like this. This force on charge 2 by 1 kind of is pushing to the left. In other words, it has an x component of the force. And it is kind of pointing down. In other words, I have a y component of that force. Similarly, if you look at the other force, you have an x component only for that force. And if I ask then how to find the total force, an actual numeric quantity for the total force, you can kind of see that I'm going to have to do some sort of a sum of the forces in the x direction to get an x component, and I'm going to have to do a sum of the forces in the y direction to get a y component. And basically what we're saying is we're going to have to add as vectors. So this is going to require vector addition, the mathematical side of vector addition, to be able to solve for the total force on an object when more than two charges are present. Okay, let's go now and take a look at our electric field. Okay, we'll look at one positively charged particle, and we can ask the question, what does the electric field look like around this particle? And you know from your studies that the electric field points away from a positively charged particle. So you have something like this, where that represents the general electric field. Now, in truth, what we want to do is we ask questions that are more specific than that. What we want to say is, what is the electric field at some point? So in this case, we could label this point, let's say point P. And I would like to know what is the magnitude of the electric field at this specific location in space. And if we want to know that magnitude, then we have an equation for the electric field. The basic relationship for the electric field, I should say, it's the same relationship that we used above, it's the electric force per unit charge for a particle. But you notice we're just picking out a point in space. We're saying what is the electric field at this point in space. So there aren't two charges. But you can kind of see here what happens is if this is the equation here for the electric force, and I divide out one of the charges, it's pretty clear here then that I'm going to come up with a relationship that looks something like this, that I get a K Q over R squared, where Q now is the charge of the source charge. It's the charge of the, it's the charge that is creating the field at point P. The radius, of course, is just the distance between the point in space that I've identified and the center of the object that is producing the field, something like this. Now, I should emphasize here, this equation was already given above. The basic relationship for the field being, the electric field being the force per unit charge. This other relationship, which is how you calculate the field for point charges, is not given. You just have to do the algebra as I did. In other words, you just have to do this substitution of this into here and divide out one of the Q's to be able to make that calculation. The red box is what you're actually given on the equation sheet. Now, to make this problem just a little bit more difficult, what we could do is we could ask, well, if I add another charge here, so in this case right here, the situation down below, I have two charges, and I can still ask the same sort of a question. I can say at this point in space, let's say right here, this little point P, I would like to know what's the total electric field at that point. Now, if we were to do this graphically, we know that the electric field at P, because of the positive charge, points away from the positive charge. So I have some kind of, we'll call it E1 here. We could go back and label our particles particle 1 and particle 2. And then we can also say, well, I also have an electric field, though, because of 2. And the electric field for a negative charge particle points in towards the charge, something like this. So I end up here with some sort of an electric field 2. And now my question is, what's the total electric field at this location? Well, once again, we can do our graphical mode for figuring out how to add those two vectors. And those two vectors, you should know when they add together, are going to give you a resultant vector that looks a little something like this. And that would be maybe our total electric field at that location in space. And how could we come up with the mathematical quantity for that, the actual numeric value? And you can see we're back to vector addition, where we're going to do something like this. We're going to take field, let's say number 1, and we're going to say, well, E1 kind of has a component that's pointing in this direction. That would be E1 in the x direction. And it kind of has a component in the y direction, E1 in the y direction. And now coming over to E2, E2 points partly to the right, E2 in the x direction, and it points partly in the vertical direction, something like this. And you have E2 in the y direction. And you can kind of see here that we're going to do the same thing as we did with forces. If we want to find the total field here, we're going to have the sum of the electric fields in the x direction and the sum of the electric fields in the y directions. And these will be the two components for my total vector, which we'll add again as vectors. Now, one thing to notice here is with particularly with the situations that you deal with all the time on the AP exam, most of the time they will have the geometry set up, and you can see in this case that this would be a good example of that, where some of the components actually cancel out. So you can kind of see here, since the point I chose was equidistant from our two charges, and the two charges in this example, let's say they had the exact same charge, then the two horizontal components would be equal in magnitude and would actually cancel to 0. The two y components would be equal in magnitude and add, since they both point in the negative y direction. And so you can kind of see there that a lot of times when you're working these problems on the actual AP exam, things will simplify once you actually do your drawing. You see that some of the components of your vectors will cancel out, making things a little more simple.